Salut tout le monde, welcome back to another differential geometry stream. I'm Anthony, and today we are going to start reading from chapter 4 now of Differential Geometry by Erwin Kreyszig. In the last video, we finished reading chapter 3, which touched on the first fundamental form, dove into basics of tensor calculus, and now we're going to start off with the second fundamental form now. And now I'm going to do a segment that I've been putting off for a couple of weeks, and that is reading, reacting, and responding to comments from viewers like you. So this week's audience award comment goes to Ivan Joro Medina 4010, and this comment was not on the most recent video, but it was actually on my first video, which was asking ChatGPT an easy differential geometry problem. And so this problem I'm going to reread so that we can have some context here. And if you haven't watched that video, it was the first differential geometry video that I had in this series. And so if it weren't for that video, then we wouldn't be here today. But I actually didn't start reading this book straight from the beginning. I started off with this problem 7.1. Sort of the whole idea behind that video was to show that for all of the AI hype that's going around, there still is a place for humans to think and reason in the mix, that if you're not a complete idiot, that in a world where AI is rolling out, you still have a role to play with your own human intelligence, so to speak. So the whole idea was to dig into this problem and to try to make it obvious that our human reasoning about this problem is better than what just kind of mechanically gets spat out by ChatGPT. So the problem 7.1 goes as follows. A one-to-one and continuous image, that is a topological image of a segment, is called a Jordan arc. One should perceive that the two conditions, namely being one-to-one and then being continuous, are both necessary in order to exclude point sets which are two-dimensional. So the problem is two-parted. The first part is to prove that the interval where t is greater than but not equal to 0, but then t is also less than or equal to 1, can be mapped in a one-to-one manner onto the square defined by x1 being greater than 0 and then x1 being less than or equal to 1, and then for x2 being greater than 0 and less than or equal to 1. And this is a square, of course, that's in an x1, x2 plane. Then the second part of the problem is that the interval where t is greater than or equal to 0 and less than or equal to 1 can be uniquely and continuously mapped onto the square x1 greater than or equal to 0, less than or equal to 1, and x2 greater than or equal to 0 or less than or equal to 1 of the x1, x2 plane. So the first part of the problem, the proof, is to look at functions which do this mapping in a one-to-one manner, and then the second part, look at mappings which do it in a uniquely and continuous manner. So in the video, I only went over really the first part, which is the one-to-one manner, and this is partly addressed by Ivan Joro Medina's comment, which I guess I'll read now. So first they say, I think you forgot to read the next phrase to what you read in 2641, and this is referring to me reading the actual solution. So as we remember perhaps from the video I made before, the function used to prove the first part that's in the solution in the book is to take the infinite decimal representation of a real number and you assign, let's say, the even indices of that decimal expansion to correspond to the first dimension of your mapping, and then you look at the other indices. If you chose odd before, choose the even now, or if you chose the even before, you chose the odd ones now to correspond to the other dimension of the mapping. So then after explaining that, the solution goes on to say, our problem illustrates the fact that the dimension of a geometric configuration is not necessarily invariant with respect to one-to-one mappings, which is what you wanted from the problem in the first place. The discovery of this fact by George Cantor in 1873 had far-reaching consequences for the development of geometry. And then this is the part that Ivan Joro Medina said that I skipped. The earliest general proof of the fact that topological mappings preserve the dimension was given by L.E.J. Brouwer in 1911. So thank you for pointing out that I skipped that. I also then continued to skip the answer to the second part of the problem, which involved looking at mappings that are unique and continuous. And so for this one, it introduces space-filling curves which I'm not going to read the solution for the sake of getting to the chapter 4 stuff that I'm going to read today. But basically it calls these space-filling curves piano curves, which actually are known better as Hilbert curves, which leads me to the rest of Ivan Joro Medina's comment. The things that ChatGPT answered were probably wrong, but the thing about dimension is right. The only thing that is missing here for the function of the problem is that its inverse is not continuous, so it's not a homeomorphism, which in this case would fail. There's a theorem called the invariance of the domain, which states that Rn is homeomorphic to Rm if and only if n equals m. But as the problem doesn't require the function to be a homeomorphism, then there is no problem with the dimension. P.S. I forgot to mention that to give a consistent definition of dimension, you can work with the Hausdorff dimension. In this case, it can be proved that the image of the Hilbert curve, which that's the piano curve which is shown in the book, has Hausdorff dimension equal to 2, so it preserves the dimension as I said above. Topologists as Brouwer and Hausdorff wanted a topological dimension that gave the right answer to the common Rn spaces and was a topological invariant for all nice enough spaces. But as you are not working with a homeomorphism, this is not a hallucination of ChatGPT. That is correct. So ChatGPT is right, but not for the right reasons. Nice video though, and I hope this helps. Thank you for the comment. It does help. So yes, as I said in the video that I made, I said that ChatGPT not answering the question correctly was sort of like a hallucination, which is incorrect because the function that it gave before was like t squared or something like using the input parameter t, and then you have a two-dimensional answer for your function where the first entry is t and then the second entry is t squared. And then for just the first part of the problem where you're looking at the one-to-one aspect, then that function did satisfy it, but then when you bring in all the stuff about dimension, that's kind of where this came out of. So right, it's not a hallucination. It could have probably been avoided with more clear terminology about the word definition, which is what was the crux of this comment, I feel like, with bringing up the things about Hausdorff dimension and mentioning Hilbert curves, which Hilbert curves, I would recommend their Wikipedia page. Very interesting stuff, great graphics. Anyways, so thank you, Ivan Joro Medina 4010 for your comment. You get the audience comment award for the week. So also in my last video, there was something that I missed saying that I wanted to say, which is about the history of tensors. So actually, Levi-Civita had correspondence with Einstein. This is going back to the whole like Newton and Einstein stuff from the last video. So Levi-Civita, who was really deep in the differential geometry field, had correspondence with Einstein, and I wanted to mention that Einstein said to Levi-Civita, "I admire the elegance of your method of computation. It must be nice to ride through these fields upon the horse of true mathematics, while the like of us have to make our way laboriously on foot." Which brings us to some more audience comments from someone who comments regularly on these videos, and I really appreciate their insightful, detailed comments. We have comments from Vanderhagen, the Stampede, riding in on the horses of these comments, the striated, thick, engorged, voluptuous steeds that Vanderhagen the Stampede is riding in upon. We had comments digging into covariant and contravariant vectors. We had a spoiler involving geodesics. It's a spoiler because, of course, in the later chapters we're going to be talking about geodesics, so we haven't talked about them already. But when Vanderhagen the Stampede brought up geodesics in their comments, I was like, you know what? I'm going to refer to light being the metric of space-time, because the ray of light that is not interfered upon by other electromagnetic waves represents the space-time. It's a geodesic, right, in space-time. They brought it up in their comment. I was like, I'm throwing it in the video. But anyways, this is all just to say, Vanderhagen the Stampede, you get an award again for just regularly making great comments. But there was a question in one of Vanderhagen the Stampede's comments that I want to get to. We have this one where it starts off, "Could you help me with these concepts?" And seemed a little bit like a test because this person already clearly knows what they're talking about. But the question in it that I really felt like addressing is, it goes on and says, should inner product be used only where the result is a scalar? No. The key here, I think, is to make sure that you're clear when you're talking about either inner product specifically as like an operation where you're interested in what results from that operation. Like if you're doing doing an actual dot product, or if you're actually like doing an inner product on two tensors, let's say. But sometimes inner product can be referred to within the context of like an inner product space, where you're more interested in the properties of inner products and related concept of norms. You're concerned about those properties and how they are in those spaces of interest, because then that enables you with those inner products and norms to develop notions of things like lengths, angles, areas, etc. So I think just being clear about what you're talking about with inner product, whether it's an operation or whether you're looking at the properties with respect to like normed vector spaces, that's the key thing. I also think, though, the other thing is sort of going with like keeping math from being just about like defining things in and of themselves, coming up with equations and tools just because they're abstractly, conceptually valid in a way, but they don't have any actual real world application. I try to stay away from that. So in order to clarify these things, it would help to have like concrete examples, you know what I mean? Like just saying what the difference between an inner product as an operation and then inner product focusing on the properties and how that can enable you to do other calculations involving like vector spaces or whatever, really comes down to having an actual application or problem to then really dig into that in greater detail with. So yeah, I mean, Vanderhagen the Stampede though, great comments, saying things like contravariant vectors, components calculated from parallel projection, covariant vector, components calculated from perpendicular projection. Just lots of value with the comments. Keep it up, my friend. Yeah, so we also have some more regular comments from .v cross with a very like seems geometrical username, you know, dot product cross product, right? We have also with .v cross's comments, there's kind of like a free associative aspect to them, which I really enjoy. We have here, I have met many students that could only point to the Latin symbol and have no idea how to pronounce it. That was me in my early math education. Too proud to ask, where was AMVs a decade ago? Actually, does that mean AMV for Anthony Makes Videos? Because if we're wondering where I was a decade ago, I was actually in the same town that I'm in now, but I was during my undergrad, and I was 10 years ago, the internet, social media, and like technology was different, of course. I mean, that goes without saying. But like, as far as YouTube goes, I think 10 years ago, that was the heyday of what we would think of now as like cringe vlogging. Like it wasn't nearly as cringe or as saturated now as it was back in 2014. I also think that like social media fitness was like the #1 like niche area on social media. So like 10 years ago, if you were doing fitness vlogging content, you were like the on YouTube 10 years ago. And part of that is like, A, you have to have the physique to begin with, but then also B, having like all the pieces and parts in place for like what would be like a modern YouTube channel production. So like the camera and the laptop to do the editing and running your channel off of and all that, and then like having, your social media all set up with each other. As far as like iPhones and stuff, right, there wasn't the technology to do streaming or like direct uploading straight from your phone really yet. Like things were still really in the like Snapchat kind of days where like you couldn't do like huge long form, like, uploading videos to web servers, right? But now like phones have come a long ways, and then like everyone has gotten into vlogging and stuff. But what that means for like internet culture being more cringe is one thing, but from like an economic market perspective, it's made the technology like cameras and stuff like easier to use because now it's cheaper because there's such a huge market. It drives the price of all this kind of stuff down, right? But then also with like, the last couple years, I feel like more niche content has grown in a way where like it's a result of like, we live in the wake of presidencies of using Twitter and stuff and all that, and so like social media has gone in this direction towards more like small niche audience creators now only recently, where I feel like if I tried to do all this stuff 10 years ago, the technology would have sucked because I couldn't do things off of my phone, like make memes and stuff. There was no community tab on the channel. It was expensive to get this phone and stuff, and like the laptop that I use for editing editing and stuff is like way faster than what I would have had access to if I would have been like the richest person in the world in 2014. Yeah, and I was an undergrad and I didn't have the intellectual maturity yet that I do now. I mean, I'm not like intellectually mature by any means, but I'm more intellectually mature than I was back then. Like 10 years ago, I was going into my junior year, I guess, third year of undergrad. I think maybe I had seen real analysis already, but then maybe only now was, 10 years ago going into the fall of 2014. Maybe then I was gonna take abstract algebra. And then certain things like even topology, like I took an undergrad topology class, but it didn't use the Moncrief's topology book, which is like the Bible of topology. So it was like, there's things that I had to read on my own, I guess, in order to get to the point where I could read differential geometry now. So, and I was way more broke than I am now, obviously. I mean, I don't know if that's obvious or not, but hopefully it is. What was I gonna say? Oh yeah, I was about to get fired actually for the first time. I was working at this job fixing phones in the mall nearby here. It's not a place in the mall anymore now, but from their perspective, I could see why they fired me, which is that there were certain kinds of techniques, such as like at the time Android phones, you would have to like heat up the glass just enough so that the LCD screen, because there's like an LCD screen that's like lighting up the pixels, and there's like a piece of glass on top, right? So sometimes when people's phones would crack and stuff, it would just be that glass, right? And so it's cheaper just to put on a new piece of glass from a materials cost point of view than to just like replace the whole entire LCD glass enclosure, right? So you'd basically have to aim a heat gun at the broken phone, but if you heat it up too much, you would crack that LCD screen underneath, right? So you had to heat it just enough so that you could get the glass, kind of like melt the glue underneath, if you want to think of it that way, melted, and then you'd have to slice it off again without cracking the glass so that it stabs the LCD screen. Once you peel it off completely, then you can lay down new glass and then you seal it on under like an ultraviolet light. So I would avoid doing those, and I would just try to do like iPhones where it's just like unscrewing the stuff out and you pull it out, put a new one in, screw it all back together kind of thing. You don't have to worry about that heat gun stuff. Anyways, or also I kind of just like didn't really fit in with the other guys who worked there. Like they were all like buddies outside of work kind of thing, and would like go to Red Rocks shows together. And it's not that I didn't, like I wanted to be invited. That was the thing, is I didn't want to do that kind of stuff. I would just want to do my own thing. I would show up, I would want to read books at work, I would want to do homework and stuff like that. Anyways, I would have watched and commented sooner, but I was responding to a beam by Scotty. We watched episode 16 today. I set the record straight. Einstein, while working in the patent office, kept getting knocked over by a light clock. That's how he came up with the whole thing. Awesome. I guess we have a returning viewer. We have Tom QZ8XW, former winner of an audience award comment, which was correcting me about C with a superscript infinity. Love your videos. Thanks, Tom. Glad to see you again. And we have more .v cross. So this is in the basics of tensor calculus video. At 1 minute and 43 seconds, I struggled to understand the outer product. By definition, the outer product contains both the inner product and determinant, commutator, cross product, etc. A equals vector ABC, Z equals vector XYZ, then the outer product is a 3x3. Trace equals inner equals AX plus BY plus CZ. The remaining 6 blocks, just one subtract the other in a special order, it is visually pleasing. That is why I'm not doing it for you. Thus 3 block for the inner and 3 commutators, and all 9 blocks are accounted for. Yeah, outer product, you make a bigger data structure in terms of like the dimensions, the size of the actual structure itself, not the bigger as in the entries of it are greater magnitude. And yeah, then at 2828, Newton high-fives Emmy, allegedly, exactly. Another .v cross comment that I feel like reading. In the highbrow community of topology, they talk about the circle group, loop space, and wedge sum. The known 2D example is this. BC, bunch of circles, wedge sum of BC equals bouquet of n circles, each petal of n rows, or a singular case of a cyclic harmonic curve. Any connected graph is homotopy equivalent to a rose. See the Wikipedia page for rows as it relates to topology. Hey, I got this connected graph. Other person, awesome. I this other graph. The circle defined by x squared plus y squared equals 1. Given some generic x on the circle, is there a generic y with the same value anywhere? Forget at any theta. Anywhere. Yes, of course. There's a generic x with the same value as some generic y value within the loci of a circle. That is homotopy. Yeah, go look at the Wikipedia page for Rho's topology. Again, that's like, you know, I gotta really brush up on the topology. I've got it back here, right here, Monkrez topology. Gotta get into that one a little more. BK3783, enjoyed this video, brother, especially the zesty intro. Looking forward to the next one. Thank you. We had another one from Vanderhagen the Stampede. I believe that the essence of differential geometry lies in its capacity for abstraction. By abstraction, I mean the ability to conceptualize representations of objects without conflating the objects themselves with their representations. Additionally, it involves abstracting concepts in such a way that their relationships remain valid as long as they maintain internal consistency. And to that I say, let's all do some object-oriented C++ programming, and let's add a little bit of encapsulation in there. And then when we're running into compiler errors and we're debugging, we'll really be thinking about maintaining internal consistency with that one. But another good comment, or I mean, these are all good comments, but comment here we have from Haldane's Ghost. Just 10 seconds in, I've never unconditionally subscribed to someone so fast. Thank you. Glad you like the the intros, and I'm gonna try to do more freestyles and stuff in the next ones. But anyways, we also have a Russian comment here. I'm gonna try to do my best to read this Russian. Jest tensory, and I think I looked it up on Google Translate. That means this is brutal tensors. And yeah, if you guys, you know, throw your comments from other languages in there, I'd love to see it. I tried to learn Russian before, years ago. I mean, I'd still be open to learning it today, but the real impediment is having a Russian speaking community that I can vibe with. I mean, if you guys picked it up, I know French. I learned that as a kid, so I feel like I'm semi-fluent-ish now, because like I say semi-fluent-ish because like I can read fluently, so I could read like at least a high school level. I definitely, there's like holes in my vocabulary where I look up words sometimes where like if I were a truly fluent person, I would hear and interact with those words so often that I wouldn't need to look them up. But then the other thing is that there's not a lot of French speakers, so my listening isn't like very developed, I don't think. And then I can talk to people, but like it's very rare that I'll meet someone in day-to-day life who speaks French. So like I'll be able to talk to them in French, but you know, it's like, is that a good enough test of whether or not I'm fluent? I don't know. But so I think I could learn Russian as an adult hypothetically, but I feel like the key really is being with other people who speak that language. So like if I flew to Russia now, I would learn Russian a lot faster than if I studied with a book every single day, did flashcards. And so being that today, chapter 4, we're starting off with the second fundamental form, I figured it'd be good to do a little bit of a recap of the first fundamental form. What is that? It was from section 27. You can go back, and it's one of the more watched, more viewed episodes in this series so far. So if you have a curve on a surface given by capital S with a vector parametric representation x in terms of u1 and u2, where u1 and u2 can be functions in terms of a parameter t, and namely if we define vectors x1 and x2 to be partial derivatives of this vector parametric representation of the curve in terms of each of these coordinate dimensions respectively. So x1 would be partial x partial u1 and x2 would be partial x partial u2. Then the first fundamental form, ds squared, where we're using the Leibniz lowercase d infinitesimal notation, because really these are indicating infinitesimal displacements on these curved surfaces and implicitly manifolds, right? So we have ds squared is equal to the dot product of x1 with x1 times du1 squared plus 2 times the dot product of x1 with x2 times du1 and then times du2 plus the dot product of x2 with itself times du2 squared. Similarly, when we introduce the notation where if we have the dot product of x sub alpha and x sub beta, we could represent that as g sub alpha beta. This could lead to a representation of the first fundamental form as g sub 1 times du1 squared plus 2 times g sub 1 times du1 times du2 plus g sub 2 times du2 squared. We also have what is known as the Gaussian notation, or as from a hater comment which I went over a few weeks ago, this is the preferred notation of Scotty Chen, where if we have g sub 1 equal to capital E, g sub 1 which is the same as g sub 2 setting that equal to capital F, and then setting g sub 2 equal to capital G, then we can represent the first fundamental form as ds squared equal to capital E times du1 squared plus 2 times capital F times du1 times du2 plus capital G times du2 squared. And this is not to get confused with the discriminant of the first fundamental form, which is also represented using a lowercase g, but there are no sub or superscripts, and this lowercase g is equal to the determinant of a lowercase g with the subscript alpha beta. So this is given by, if we have in the first column of the determinant g sub 1 then g sub 2 and then in the second column of the determinant g sub 1 and then g sub 2 and a requirement for this determinant is that the cross product of x1 and x2 is non-zero. It turns out that this determinant is positive. This was shown in an earlier section. But what is this used for? We can write a formula for the area of a portion of a surface in terms of a double integral of a function of this discriminant of the first fundamental form, namely capital A of capital H, where capital H is the portion of the surface, is given by the double integral on capital U, which is the domain corresponding to the portion of the surface, double integral of the square root of G, being this discriminant of the first fundamental form. And these double integrals are in terms of du1 and then du2. So that's the first fundamental form. And in the previous chapter, chapter 3, we also, obviously, if you didn't catch it from a little bit of the comments, we went over the basics of tensor calculus. So we are now in chapter 4, second fundamental form, Gaussian and mean curvature of a surface. Section 38, second fundamental form. In this and the following 3 sections, we will consider the geometric shape of a surface in the neighborhood of any of its points. Of course, this problem is of fundamental importance. In this connection, it is natural to start from the consideration of the curvature of curves on a surface. We first state the following simple fact. At any point of a curve capital C on a surface capital S, the corresponding unit normal vector n to capital S lies in the normal plane to capital C, which also contains the unit principal normal vector P to capital C. The angle between these two vectors will depend on the geometric shape of capital C and capital S in a neighborhood of the point under consideration. Thus, for any plane curve, the vectors P and N are orthogonal, as shown in figure 44. In the case of a circle capital C through a fixed point capital P of a sphere capital S, vectors P and N lie in the same line if and only if capital C is a great circle. Assuming that N is directed towards the interior of the sphere, the angle between the vectors P and N increases with decreasing radius lowercase r of capital C, as shown in figure 45. We now consider an arbitrary surface capital S with a vector parametric representation x of u1, u2 of class r greater than or equal to 2, that is to say it is at least 2 times differentiable in terms of these dimensions u1 and u2. And on capital S, an arbitrary curve capital C, u1, which is given by a function u1 of s, and similarly u2, which is given by a function u2 of s, of class r greater than or equal to 2, where s is the arc length of capital C. We denote by gamma the angle between the unit principal vector p to capital C and the unit normal vector n to capital S. Since the vectors p and n are unit vectors, we have that the cosine of gamma is equal to the dot product of p and n, where kappa is greater than 0. The value of this scalar product will, in general, vary along the curve capital C. Since the vector p equals x double dot over kappa, see section 15, which is on the Frenet equations, we find that kappa times cosine of gamma is equal to the dot product of x double dot and n. And just a reminder, when there's the fly dot notation for derivatives, this means a derivative in terms of arc length s. We again use the notation where x sub alpha equals partial x partial u alpha and x sub sub alpha beta equals partial squared x partial u alpha partial u beta. Now, x dot equals partial x partial u1 times partial u1 partial s plus partial x partial u2 times partial u2 partial s, which equals x sub alpha times u dot alpha. And by differentiation, x double dot equals x sub alpha beta times u dot alpha times u dot beta plus x sub alpha times u double dot alpha. Now, the scalar product of x sub alpha and n equals 0. Therefore, from the preceding expression, the scalar product of x double dot with n is equal to quantity x sub alpha beta scalar product with n closed quantity times u dot alpha times u dot beta. We now introduce the important abbreviated notation b sub alpha beta equals the scalar product of x sub alpha beta and n, where alpha can equal to 1 or 2 and beta can equal 1 or 2. The values of these scalar products depend on the surface capital S, but are independent of the curve capital C on capital S under consideration. Since x sub alpha beta equals x sub beta alpha, the quantities b sub alpha beta are symmetric, namely b sub alpha beta equals b sub beta alpha. The quadratic form b sub alpha beta times du alpha times du beta, that is b sub 1 1 times du 1 squared plus 2 times b sub 1 2 times du 1 du 2 plus b sub 2 2 times du 2 squared, is called the second fundamental form. In addition to the previously introduced abbreviated notation, the notation b sub 1 1 equals capital L, b sub 1 2 equals b sub 2 1, which is then set equal to capital M, and b sub 2 2 equals capital N, can also be found in literature. Then the second fundamental form is given by the expression capital L times du1 squared plus capital 2 times capital M times du1 du2 plus capital N times du2 squared. For reasons similar to those mentioned in the section on the first fundamental form, we will use the notation where b sub alpha beta equals the scalar product of x sub alpha beta and n exclusively. Differentiating the orthogonality relation, the scalar product of x sub alpha with n equals 0, we have that the scalar product of x sub alpha beta with n plus the scalar product of x sub alpha with n sub beta equals 0, where n sub beta is equivalent to partial n partial u beta. By comparing this with the relation b sub alpha beta equals the scalar product of x sub alpha beta with n, we obtain the important relations where b sub alpha beta equals the scalar product of negative x sub alpha with n sub beta. From the integral for arc length and the first fundamental form, we find that ds squared equals g sub alpha beta times du alpha times du beta, which is equal to the scalar product of dx with itself. From the previous relation for b sub alpha beta, we obtain analogously b sub alpha beta times du alpha times du beta equals the scalar product of negative dx with dn. The second fundamental form is therefore invariant with respect to any allowable coordinate transformation which preserves the sense of the vector n. Since the coordinate differentials du alpha have a contravariant transformation behavior, as shown in the section on contravariant and covariant vectors, and the second fundamental form is invariant, the coefficients b sub alpha beta of this form are the components of a covariant tensor of second order with respect to these coordinate transformations. Now let lowercase t be any allowable parameter of the above curve capital C. Then u alpha dot is equal to du alpha dt times dt ds, which is equal to u alpha prime, where the prime is on the alpha superscript, over s prime. Hence, in consequence of the second fundamental form, then the relation kappa times cosine gamma equal to the scalar product of x double dot and n takes the form kappa times cosine gamma equals the fraction with the numerator of b sub alpha beta times u with the superscript alpha prime times u with the superscript beta prime over a denominator of s prime squared. This fraction is then equal to another fraction with a numerator of b sub alpha beta times u with the superscript alpha prime times u with the superscript beta prime, and then the denominator g sub alpha beta times u superscript alpha prime u superscript beta prime. Or kappa times cosine gamma equals a fraction with the numerator b sub alpha beta times du alpha times du beta, and then a denominator g sub alpha beta times du alpha du beta. Because of the formula for the unit normal vector to capital S at a point capital P, we can represent the coefficients b sub alpha beta of the second fundamental form in the following manner. B sub alpha beta equals the scalar product of x sub alpha beta with n equals then the scalar product of x sub alpha beta with the quantity, which is a fraction, numerator being the cross product between x1 and x2, and the denominator being the square root of g, closed quantity. Hence, b sub alpha beta equals the reciprocal of the square root of g, then times the determinant with the first column being x1, the second column being x2, and the third column being x sub alpha beta. While the first fundamental form is positive definite, as shown in the section on properties of the first fundamental form, the second fundamental form may vanish, as we shall see in the following section. The discriminant b equal to b sub 1 1 times b sub 2 2 minus the square of b sub 1 2 of the second fundamental form will be considered in a future section on elliptic, parabolic, and hyperbolic points of a surface. Problem 38.1. Determine the second fundamental form of a surface represented in the implicit form x sub 3 equals capital F of x sub 1 x sub 2. We set x1 equal to u1 and x2 equal to u2. That is, the vector x of u1 u2 equals u1 in the first entry, u2 in the second entry, and in the third entry the function capital F of u1 and u2. Then the vector x1, which is equal to in the first entry 1, the second entry 0, and the third entry f sub u with the u having a superscript 1, and then x2 vector equals in the first entry 0, in the second entry 1, and in the third entry f sub u with itself, the u having a superscript 2, and then the vector x sub alpha beta equals in its first two entries 0 simply, and then in the third entry f with a subscript of u superscript alpha u superscript beta as the entire subscript. And then we have that g is equal to 1 plus the square of capital F sub u1 plus the square of capital F sub u2. Now we also have that b sub alpha beta is equal to the reciprocal of the square root of g times a determinant where the first column is 1 and then the rest zeros, and then the second column is 0 1 0, and then the third column is f sub u1, f sub u2, and then f sub u alpha u beta. And this b sub alpha beta is all equal to a fraction with a numerator of capital F sub u alpha u beta, and then a denominator which is the square root of the quantity 1 plus the square of fu1 plus the square of fu2 closed quantity, where in all of this capital F sub u alpha is equivalent to the partial derivative of capital F in terms of u alpha, let's say. We replace u1 and u2 again by x1 and x2 respectively. The second fundamental form is then given by the expression we have in the numerator the quantity f sub x1 x1 times dx1 squared plus 2 times capital F sub x1 x2 times dx1 dx2 plus capital F sub x2 x2 times dx2 squared. And then in the denominator we have the square root of the quantity 1 plus the square of f sub x1 plus the square of f sub x2, where capital F sub x alpha is equivalent to the partial derivative of capital F in terms of x alpha, etc. Problem 38.2. Prove by direct calculation that the coefficients of the second fundamental form are the components of a covariant tensor of second order with respect to coordinate transformations which preserve the sense of the unit normal vector n. Let u alpha be given by the function u alpha in terms of u over bar 1 and u over bar 2, where alpha can be 1 or 2, and let this be an allowable coordinate transformation which preserves the sense of the unit normal vector n. We denote by b over bar sub alpha beta the coefficients of the second fundamental form with respect to the coordinates u over bar sub 1 and u over bar sub 2. Then, because of the relation b sub alpha beta equal to the scalar product of negative x sub alpha and n sub beta, as well as the transformation law for covariant tensors, b over bar sub alpha beta is equivalent to the scalar product between x sub alpha over bar beta over bar and n, which is then equal to the scalar product of negative x sub alpha over bar and n sub beta over bar, which is then equal to the scalar product of negative x sub mu with n sub mu, then times partial u mu, partial u over bar alpha times partial u nu, partial u over bar beta, which is equal to b sub mu nu times partial u mu, partial u over bar alpha times partial u mu, partial u over bar beta, where x sub alpha over bar is equal to the partial derivative of x in terms of u over bar alpha, etc. Indeed, these relations are of the form of an allowable transformation for a covariant tensor of second order. number. Section 39, arbitrary and normal sections of a surface. Meusnier's theorem, asymptotic lines. We are going to study the geometric shape of a surface S in the neighborhood of any of its points. For this purpose, we have considered curves on S passing through a point of S. We have obtained the important relation kappa times cosine gamma equals fraction with the numerator of b sub alpha beta times u alpha dot times u beta dot all over a denominator of g sub alpha beta times u alpha dot times u beta dot, which is equal to a fraction with the numerator of b sub alpha beta times du alpha times du beta, and then a denominator of g sub alpha beta times du alpha times du beta, where kappa equal to a function kappa of s is the curvature of a curve capital C given by u1 equal to the function u1 of s and u2 equal to the function u2 of s on a surface capital S, which is given by a vector parametric representation x of u1, u2, and gamma equal to the function gamma of s is the angle between the unit principal normal vector p of s to capital C and the corresponding unit normal vector n of u1 of s and u2 of s to capital S. We will now find a geometrical interpretation of this relation for kappa times cosine of gamma. Obviously, the direction of the unit tangent vector t equal to x dot equal to x sub alpha times u alpha dot to capital C is determined by the ratio of u1 dot to u2 dot. If we consider any fixed point capital P of capital S, the values of the coefficients g sub alpha beta and b sub alpha beta of the fundamental forms are fixed, that is, independent of the special choice of the curve capital C on capital S passing through P. This means that the curvature kappa of capital C at capital P depends only on the direction of the unit tangent vector and of the unit principal normal vector to capital C at capital P. Since these vectors span the osculating plane, we have Theorem 39.1. All curves of class r greater than or equal to 2 on a surface capital S which pass through any fixed point capital P and have at capital P the same osculating plane, which does not coincide with the tangent plane of capital S at capital P, also have the same curvature at the point capital P. The set of these curves includes a plane curve, namely the curve of intersection of capital S and the common osculating plane of the curves at capital P. We may therefore restrict our investigation to plane curves on capital S. We can draw further conclusions from the relation for kappa times cosine of gamma. For this purpose, we consider all curves whose tangents at the point capital P have the same direction. If this direction is fixed, the right-hand side of the relation is constant. That is, the curvature of these curves depends only on the angle gamma between their unit principal normal vector P at the point capital P and the corresponding unit normal vector n to capital S. Hence, for those curves which have at the point capital P the same direction, the following relation holds. Kappa times cosine of gamma is equal to kappa sub n, where kappa sub n, when a fixed tangent direction has been chosen, is a constant. Kappa sub n can be geometrically interpreted as follows. If gamma equals 0, then kappa equals kappa sub n. If gamma equals pi, then kappa equals negative kappa sub n. The magnitude of kappa sub n is therefore the curvature of the curve of intersection of the surface capital S and a plane passing through both the tangent to the curve at the point capital P and the normal to capital S at capital P. Curves of this type are called normal sections of capital S. The value of kappa sub n depends only on the direction of the tangent to the normal section at capital P. Kappa sub n is called the normal curvature of capital S at capital P, corresponding to the direction of the tangent under consideration. We introduce the normal curvature vector lowercase k sub n equals kappa sub n times vector n. From the relation for kappa times cosine of gamma given in terms of the first and second fundamental forms, as well as the relation for kappa times cosine of gamma, which is equal to kappa sub n, we obtain that kappa sub n is then equal to b sub alpha beta times du alpha times du beta all over g sub alpha beta times du alpha times du beta. That is, the normal curvature is the quotient of the second and first fundamental forms. It should be noticed that the sign of the normal curvature is immaterial. We remember that the sense of the vector n depends on the choice of the coordinates on the surface capital S, as we went over in section 34, which was on normal to a surface. If we introduce coordinates on capital S so that at capital P the vector n and the unit principal normal vector P to a normal section coincide, then gamma equals 0, and the curvature kappa of capital C at capital P is equal to the corresponding normal curvature kappa sub n. If we change the sense of the vector n, then gamma equals pi pi and kappa equals negative kappa sub n. Since we will only be interested in comparing the values of the normal curvature corresponding to different directions at capital P, we could have defined the normal curvature by negative kappa sub n as well as by kappa sub n. We have already stressed the fact that the normal curvature depends on the direction of the tangent to a normal section at capital P. Directions at capital P for which kappa sub n equals 0 are called asymptotic directions. A curve for which at any of its points the tangent has an asymptotic direction is called an asymptotic curve. We will consider these curves later. Excluding the case kappa sub n equals 0, we may set kappa sub n equal to 1 over capital R, where kappa sub n is non-zero. Obviously, the magnitude of capital R is the radius of curvature of the corresponding normal section at the point under consideration. Since kappa equals the reciprocal of rho, we may now write kappa times cosine of gamma equal to kappa sub n in the form rho equals capital R times cosine of gamma. In this manner, we obtain the following result, the theorem of Meusnier, which goes with figure 46. The center of curvature of all curves on a surface capital S, which pass through an arbitrary, that is, fixed point capital P, and whose tangents at capital P have the same direction, different from an asymptotic direction, lie on a circle capital K of radius 1/2 the magnitude of capital R, which lies in the normal plane and has a contact of first order at least with capital S at capital P. The circles of curvature of all plane sections of capital S with common tangent at capital P whose direction is different from an asymptotic direction lie therefore on a sphere. In consequence of the theorem of Meusnier, we may restrict our considerations to the normal sections of capital S at capital P. We will now study asymptotic directions. In consequence of the relation for normal curvature, kappa sub n vanishes exactly for those directions for which the second fundamental form vanishes. The differential equations of the asymptotic curves on a surface is therefore b sub alpha beta times du alpha times du beta, which is equal to 0. The existence of real asymptotic curves, that is, the existence of real solutions of the relation b sub alpha beta times du alpha times du beta equals 0, depends on the shape of a surface. This will be seen in the following section. The name asymptotic direction will be justified by the consideration of the indicatrix of Dupin, which is in section 42 on Euler's theorem and Dupin's indicatrix. From the relation for kappa times cosine gamma equals kappa sub n, we see that the curvature of a normal section in an asymptotic direction vanishes. By means of the formulae of Frenet, the relation kappa times cosine gamma equals the scalar product of x double dot and n, as well as the relation for kappa times cosine gamma in terms of the fundamental forms, we obtain from b sub alpha beta times du alpha du beta equals 0 that the scalar product of x double dot with n is equal to the scalar product of kappa times p with n equals 0. We thus have the following simple theorem 39.3. Any straight line on a surface of class r greater than or equal to 2 is an asymptotic curve. Thus, the generating straight lines of a cylinder or a cone are asymptotic curves on these surfaces. From what we have thus obtained, it follows that at each point of an asymptotic curve capital C, at which kappa is greater than 0, the principal normal of capital C lies in the tangent plane of the surface. From this we obtain the following important property of asymptotic curves. Theorem 39.4. At any point of an asymptotic curve capital C given with a vector parametric representation given by x of t, for which kappa is greater than 0, the binormal of capital C at the normal to the surface coincide. Consequently, at any point of capital C, the osculating plane of capital C and the tangent plane to the surface then coincide. Furthermore, in consequence of the differential equation involving the second fundamental form, we obtain theorem 39.5. The coordinate curves of coordinates on a surface are asymptotic curves if and only if, with respect to these coordinates, b sub 1 equals 0 and b sub 2 equals 0. Of course, coordinates of this type can be introduced on a surface capital S if and only if at any point of capital S there are two different real asymptotic directions. We will point out in the following section that this condition holds if capital S consists of hyperbolic points only, that is, points at which the discriminant lowercase b of the second fundamental form is negative. We finally consider two examples of Meusnier's theorem. Example 1. The normal sections of a sphere capital S are great circles. Any other plane section is a small circle. At any point, the circles of curvature are identical with the normal sections and therefore lie on capital S. Example 2. We consider the cylinder capital Z with a vector parametric representation given by x in terms of u1 and u2, which is equal to, in the first entry, r cosine u2, in the second entry, r sine u2, and in the third entry, u1, and plane sections of capital Z which pass through any fixed point, capital P of capital Z, and whose tangents at the point capital P are parallel to the x1, x2 plane. The normal section among those sections is a circle of radius r, while the other sections are ellipses whose principal axes have the lengths 2a equals 2r over cosine gamma and 2b equals 2r respectively. Here, gamma is the angle between the plane of the section and the x1, x2 plane. According to the theorem of Meusnier, the radius of curvature of those ellipses at capital P is rho equal to r cosine gamma. From this and the preceding formulae, we obtain the well-known expression rho equals b squared over a for the radius of curvature of an ellipse at the vertex which lies on the principal axis of length 2a. Very interesting. Problem 39.1. Prove that the tangent planes to a cone of revolution at the points of any of its generating straight lines coincide. Using the representation for a cone given by the vector x in terms of u1 and u2 equal to, in the first entry, u1 cosine u2, in the second entry, u1 sine u2, and in the third entry, au1, we have g sub 1, 1 equals 1 plus a squared, g sub 1, 2 equals 0, and g sub 2, 2 equals u1 squared. We also have that the vector n is equal to the reciprocal of u1 times the square root of the quantity 1 plus a squared closed quantity times the determinant, where the first column is e1, then cosine u2, then negative u1 sine u2. In the second column, we have e2 and then sine of u2, and then u1 cosine u2. And then in the third column, we have e3 and then a and then 0, where vectors e sub I represent unit vectors in the direction of the positive ray of the x sub I axis. We thus find that the vector n component-wise is given by, in the first entry, negative a cosine u2 over w, and then in the second entry, negative a sine u2 over w, and then simply 1 over w, where w is equivalent to the square root of the quantity 1 plus a squared. That is, the normal direction to the cone is independent of u1. Since the curves u2 equal to a constant are the generating straight lines of the cone, n is constant along any of those generators. Hence, the tangent planes to the cone at the points of any generating straight line coincide. Problem 39.2. Given the paraboloid of revolution capital S, which is given by x sub 3 equal to x sub 1 squared plus x sub 2 squared, determine the radius and center of the circle of curvature of the normal section of capital S at a point capital P, given by x3 equals x3 with a superscript quantity 0, whose tangent at capital P is parallel to the x1, x2 plane. The intersection of the paraboloid capital S and the plane capital E, which is given by x sub 3 equals x sub 3 and then superscript quantity 0, is a circle of radius rho equal to the square root of x sub 3 with a superscript quantity 0, which is then equal to r sub 0. This is not a formal section of capital S. The angle gamma between capital E and the normal to capital S can be obtained from the relation tangent of pi over 2 minus gamma, which is equal to tangent of alpha, which is equal to 2 times r sub 0, or r naught. Hence, cosine gamma is equal to sine of alpha, which is equal to tangent alpha over the square root of 1 plus tangent squared of alpha, which is equal to 2r naught over the square root of 1 plus 4r naught squared. According to Meusnier's theorem, we thus obtain capital R equals rho over cosine gamma, which is equal to 1/2 times the square root of the quantity 1 plus 4 times r naught squared. The center of curvature of the normal section under consideration lies on the axis of revolution. Problem 39.3. Determine the asymptotic curves of a cylinder of revolution by means of the differential equation b sub alpha beta times du alpha times du beta equals 0. The generating straight lines are asymptotic curves of the cylinder capital S, given by the theorem that any straight line on a surface of class r greater than or equal to 2 is an asymptotic curve. We will prove that those curves are the only asymptotic curves of capital S. We represent capital S in the form vector x in terms of u1, u2 equals first entry r cosine u1, and then second entry r sine u1, and then third entry u2. Then x sub 1, 1 is equal to negative r cosine u1, then negative r sine u1, then 0, and then vector x sub 1, 2 equals 0, and vector x sub 2, 1, 2 equals 0. Therefore, b sub 1, 2 and b sub 2, 2 equals 0, and the differential equation thus takes the form b sub 1, 1 times du1 squared equals 0. Since b sub 1, 1 equals negative r squared over the square root of g, which is non-zero, we must have du1 equals 0, that is, u1 is equal to a constant. Since this is the only solution of that equation, the above straight lines are the only asymptotic curves on the cylinder. Continuing on, section 40. Elliptic, parabolic, and hyperbolic points of a surface. In order to determine the shape of a surface capital S in a neighborhood of any of its points, we first considered arbitrary curves on capital S. We saw that, in consequence of 39.1, it suffices to consider plane curves on capital S. Finally, Theorem 39.2 enabled us to restrict our investigation to normal sections of capital S, that is, curves of intersection of capital S and planes which are orthogonal to the tangent plane to capital S at a point capital P under consideration. That investigation led us to the introduction of the normal curvature, given by kappa sub n, which is equal to the fraction with the numerator b sub alpha beta times du alpha times du beta and a denominator of g sub alpha beta times du alpha times du beta. The magnitude of kappa sub n is the curvature of the normal section of capital S at capital P, whose tangent direction is du2 to du1. We will now see that there are three different possible forms of capital S in a neighborhood of a point at which the second fundamental form does not vanish identically. For this purpose, we consider the behavior of kappa sub n as a function of the direction du2 to du1 of the tangent to the normal sections at capital P. As was proved in section 28, which was on properties of the first fundamental form, the first fundamental form ds squared equal to g sub alpha beta times du alpha times du beta is positive definite, that is, its value is always positive. Hence, the sign of kappa sub n depends on the second fundamental form only. This form is positive or negative definite if and only if, at capital P, the discriminant, which is given by b equal to the determinant of b sub alpha beta, which is equal to a determinant where in the first column we have b sub 1, 1, and then b sub 2, 1, and then in the second column b sub 1, 2, and then b sub 2, 2, which is thus equal to b sub 1, 1 times b sub 2, 2 minus the square of b sub 1, 2. The discriminant of this form is positive. In this case, kappa sub n has the same sign for all possible directions of the normal sections at capital P, that is, the centers of curvature of all normal sections lie on the same side of the surface capital S. Then capital P is called an elliptic point of the surface. An example: any point of the ellipsoid given by the vector x in terms of u1 and u2, which is equal to, entry-wise, a times cosine u2 times cosine u1, and then b times cosine u2 times sine of u1, and then c times sine of u2, which for more detail you can revisit problem 25.3. Any point of this ellipsoid is elliptic. If b equals 0 at a point capital P of a surface, kappa sub n does not change sign, but there's exactly one direction where kappa sub n equals 0. That is, exactly one real asymptotic direction. Capital P is then called a parabolic point of the surface, and see figure 48. Another example: any point of a cylinder or of a cone, with the exception of the apex, is parabolic. If b is less than 0 at a point capital P of a surface, kappa sub n does not maintain the same sign for all directions du2 to du1. More precisely, there exist two real asymptotic directions for which kappa sub n equals 0. These directions separate the directions for which kappa sub n is positive from those for which kappa sub n is negative. See figure 49. Capital P is then called a hyperbolic or a saddle point of the surface. Since the conditions of b being either greater than or equal to 0 or less than or equal to 0 correspond to a geometric property of the surface, they must be invariant with respect to any allowable coordinate transformation, such as u alpha given by the function u alpha in terms of u over bar 1 and u over bar 2, where alpha can be either 1 or 2. Indeed, the coefficients b sub alpha beta of the second fundamental form are the components of a covariant tensor, refer to section 38, so they have the same transformation behavior as the components g sub alpha beta of the metric tensor. The discriminant b of the second fundamental form thus has the same transformation law as the discriminant g of the first fundamental form. That is, b over bar is equal to partial u1 u2 partial u over bar 1 u over bar 2 squared times b. And I would refer back to Theorem 28.3. Since in this relation the square of the Jacobian appears, This holds for all allowable transformations of class r greater than or equal to 2, and also for those which reverse the sense of the normal vector n. From this we see that if b is greater than 0, b is equal to 0, or b is less than 0, we have also that b over bar is greater than 0, b over bar is equal to 0, or b over bar is less than 0, respectively. These results can be summed up in a table where the elliptic point, parabolic point, and hyperbolic point are separated out in terms of their discriminant b of the second fundamental form, the number of real asymptotic directions they have, and which figure they are exemplified in. Depending on the type of a point capital P on a surface capital S passes through the tangent plane capital E of capital P to capital S at capital P, or does not pass through capital E of capital P, the tangent plane that is. In order to obtain a clear picture of this important fact, we first prove the following. Theorem 40.1. Let a surface capital S be given by a representation x of u1, u2 of class r greater than or equal to 2. If at a point capital P given by x in terms of u1 and u2 of capital S, the second fundamental form does not vanish identically, then it is equal to twice the directed distance of a point capital Q, which is given by x in terms of u1 plus du1 and u2 plus du2 of capital S from the tangent plane capital E of capital P to capital S at capital P, neglecting terms of the third and higher order in the magnitude of du1 plus the magnitude of du2, and refer to figure 50, which is below. Proof. We consider a point capital Q star given by x of u1 plus h1 and u2 plus h2 of capital S. According to Taylor's formula, we have that x of u1 plus h1 and u2 plus h2 is equal to x of u1 u2 plus h superscript alpha times x sub alpha plus 1 over 2 factorial times h alpha times h beta times x sub alpha beta plus little o of the square of the magnitude of h1 plus the magnitude of h2, where the vector little o is defined as in section 11. This is a Landau symbol. And the values of the derivatives at the point capital P given by x in terms of u1 and u2 must be taken. The distance of capital Q star from the tangent plane capital E of capital P to capital S at capital P is therefore capital A of capital Q star, which is equal to the scalar product of the quantity x in terms of u1 plus h1 and u2 plus h2 minus x in terms of u1 and u2 closed quantity, and then that is scalar product with n, which this is all equal to, or capital A of capital Q star is equal to 1/2 times h superscript alpha times h superscript beta times x sub alpha beta, and then this entire product is scalar product with the vector n, and this is all plus little o, or Landau symbol, of the square of the magnitude of h1 plus the magnitude of h2, where n is the unit normal vector to capital S at capital P. Setting h superscript alpha to du alpha in consequence of the notation b sub alpha beta equal to the scalar product of vectors x sub alpha beta and n, we obtain that capital A of capital Q is equal to 1/2 times b sub alpha beta times du alpha times du beta plus little o, or Landau symbol, of the quantity magnitude of du1 plus the magnitude of du2 squared. From this theorem, we obtain immediately theorem 40.2, which is at any elliptic or parabolic point capital P, the surface capital S, considered in a sufficiently small neighborhood of capital P, lies entirely on one side of the corresponding tangent plane capital E of capital P. At a hyperbolic point, it passes through the tangent plane capital E of capital P. And now, problem 40.1. Find the differential equation of the asymptotic curves of a surface of revolution given by x in terms of u1 and u2, which is equal to u2 times cosine u1, and then u2 times sine u1, and then h of u2, and determine the location of the elliptic, parabolic, and hyperbolic points on this surface. We may locally represent any surface of revolution capital S, which is not a cylinder, refer back to problem 39.3, in the form of a vector x in terms of u1 and u2, which is equal to, then entry-wise, u2 times cosine u1, and then u2 sine u1, and then h times u2. Refer back to problem 28.1. Since lowercase g is equal to the square of u2 times the quantity 1 plus h prime squared, we find from the relation b sub alpha beta equals 1 over square root of g times the determinant, where column-wise it goes vector x1 and then vector x2 and then vector x sub alpha beta. We find that b sub 1, 1 is equal to the reciprocal of the square root of g times a determinant where column-wise it goes negative u2 times sine u1 and then cosine u1 and then negative u2 cosine u1, and then in the second column it goes u2 times cosine u1 and then sine u1 and then negative u2 sine u1, and then in the third column it goes 0 h prime and then 0. This is all equal to, or in other words, b sub 1, 1 is equal to the negative fraction with the numerator u2 times h prime all over a denominator of the square root of the quantity 1 plus h prime squared, closed quantity. We also find that b sub 1, 2 is equal to 0 and that b sub 2, 2 is equal to negative h double prime over the square root of the quantity 1 plus h prime squared, closed quantity, where, of course, primes denote derivatives with respect to u2. That is, the asymptotic curves are solutions of the differential equation u2 times h prime times du1 squared plus h double prime times du2 squared equals 0. We have that lowercase b, or the second fundamental form, is equal to u2 times h double prime all over the quantity 1 plus h prime squared. If h prime equals 0, then b equals 0. That is, points of capital S at which the tangent plane is orthogonal to the axis of revolution are parabolic points. Points at which h double prime is positive are elliptic, and points at which h double prime is negative are hyperbolic. If h double prime is equivalent to 0, then h equals c times u2 plus d. In this case, we obtain a cone of revolution. Section 41, principal curvature, lines of curvature, Gaussian and mean curvature. In the preceding section, we considered the normal curvature kappa sub n at an arbitrary fixed point capital P of a surface as a function of the direction of the tangent to the normal sections at capital P. We have obtained the following results. If capital P is an elliptic or parabolic point, the sign of kappa sub n is the same for all directions. If capital P is a hyperbolic point, there are directions for which kappa sub n is positive, as well as directions for which kappa sub n is negative. These directions are separated by the two real asymptotic directions for which kappa sub n equals 0. It is natural to ask for directions for which kappa sub n has an extreme value. This question does not make sense at points for which kappa sub n is constant, that is independent of the direction of the normal sections. Obviously, this property holds if and only if b sub alpha beta is proportional to g sub alpha beta, namely b sub alpha beta is equal to lambda of u1 u2 times g sub alpha beta, where alpha can be 1 or 2 and beta can be 1 or 2. A point of this type is called a navel point or umbilic. In this case, b is equal to lambda squared times g. Now g is positive, hence if lambda does not equal 0, we have that b is positive and the point is called an elliptic umbilic. If lambda equals 0 and also b equals 0, such a point is called a parabolic umbilic, flat point, or planar point. For details, see sections 44 and 48. Let us assume that the point capital P under consideration is not an umbilic. We first determine those directions, that is, those values of du2 to du1, for which kappa sub n has an extreme value, which we shall obtain later. Obviously, the relation for the normal curvature in terms of a quotient of the second and first fundamental forms can be written of the form quantity b sub alpha beta minus kappa sub n times g sub alpha beta, closed quantity, times L superscript alpha times L superscript beta equals 0, where L superscript gamma denotes du gamma. We set a sub alpha beta equal to b sub alpha beta minus kappa sub n times g sub alpha beta. If we differentiate the relation quantity b sub alpha beta minus kappa sub n times g sub alpha beta closed quantity times L superscript alpha times L superscript beta equals 0 with respect to L superscript gamma, treating kappa sub n as a constant because d kappa sub n is equal to 0 is the necessary condition for kappa sub n to be a minimum, we thus obtain the partial derivative with respect to L gamma of a sub alpha beta times L alpha L beta is equal to a sub alpha beta times partial L alpha partial L gamma times L beta plus L alpha times partial L beta partial L gamma closed quantity. And this is all equal to then a sub alpha beta times Kronecker delta with a subscript gamma, and the Kronecker delta has itself a superscript alpha. This is times L beta minus L alpha times Kronecker delta with a subscript gamma, and then the Kronecker delta has a superscript beta, and this is all then equal to a sub gamma beta times L beta plus a sub alpha gamma times L alpha, which then is all equal to the quantity a sub gamma alpha plus a sub alpha gamma closed quantity times L alpha. Since g sub alpha beta and b sub alpha beta are symmetric, we have that a sub gamma alpha is equal to a sub alpha gamma, and therefore the quantity b sub alpha gamma minus kappa sub n times g sub alpha gamma closed quantity times L alpha is equal to 0, where gamma can be 1 or 2. If we eliminate kappa sub n, we find that the determinant, where in the first column we have g sub 1 alpha times du alpha, and then g sub 2 alpha times du alpha, and then in the second column of this determinant we have b sub 1 beta times du beta, and then b sub 2 beta times du beta, this entire determinant is equal to 0. Or we have now a 3 by 3 determinant where in the first column we have du2 squared, and then g sub 1 1, and then b sub 1 1. In the second column we have negative du1 du2, and then g sub 1 2, and then b sub 1 2. And then in the third column finally we have du1 squared, and then g sub 2 2, and then b sub 2 2. And this entire determinant is also equal to 0. The roots of the quadratic equation given by resolving this determinant determine those directions for which the normal curvature kappa sub n becomes extreme, as will be seen in the following section. Those directions are called the principal directions of normal curvature, or curvature directions, at the point capital P under consideration. The corresponding values of kappa sub n are called the principal normal curvatures of the surface capital S at capital P. We denote them by kappa sub 1 and kappa sub 2. The centers of curvature of the corresponding normal sections are called the centers of principal curvature of the surface capital S at capital P. We will now consider the principal directions in more detail. At any regular point we have Theorem 41.1. The roots of the equation given by the 3 by 3 determinant equal to 0 mentioned earlier are real. At any point which is not an umbilic, the principal directions are orthogonal. The proof is as follows. The reality of the principal directions is obvious geometrically. We prove the orthogonality. Let L with a superscript alpha and a subscript quantity 1 and L with the superscript alpha and a subscript quantity 2 denote those directions, and let kappa sub 1 and kappa sub 2 be the corresponding values of kappa sub n. If we insert this in the 2 by 2 determinant that is equal to 0, which is given in terms of the fundamental forms, we have that the quantity b sub alpha gamma minus kappa sub nu times g sub alpha gamma closed quantity times L superscript alpha and then a subscript of the quantity nu, this is all equal to 0, where nu can be either 1 or 2. We multiply these respective equations by L with a superscript gamma and a subscript quantity 2, and L with a superscript gamma and a subscript quantity 1, sum with respect to gamma, and subtract the equations thus obtained. This yields quantity kappa sub 2 minus kappa sub 1 closed quantity times g sub alpha gamma times L with the superscript alpha and a subscript quantity 1 times L with the superscript gamma and a subscript quantity 2. This is all equal to 0. Since kappa sub 1 does not equal kappa sub 2, the principal directions are orthogonal. Refer back to the relation for cosine of gamma, the angle on a surface between two vectors, and this relation is given in terms of the first fundamental form. A curve on a surface capital S whose direction at every point is a principal direction is known as a line of curvature of capital S. Any line of curvature is a solution of the differential equation given by the 3 by 3 determinant equal to 0 read previously, which is a quadratic in du alpha. Solutions of this 3 by 3 determinant equal to 0 are such that through any point of a surface of class r greater than or equal to 3, which is not an umbilic, there pass exactly two curves which, according to the theorem that the roots of the equation given by the expansion of the 2 by 2 determinant in terms of the fundamental forms are real, and that at any point which is not an umbilic the principal directions are orthogonal. According to this, then these solutions are such that through any point of a surface of class r greater than or equal to 3, which is not an umbilic, there pass exactly two curves which intersect orthogonally. In consequence of this same theorem, we furthermore obtain Theorem 41.2. The lines of curvature on any real surface capital S of class r greater than or equal to 3 are real curves. If capital S has no umbilics, the lines of curvature form an orthogonal net everywhere on capital S. While the existence of real asymptotic curves on a surface capital S depends on the geometric shape of capital S, referred to the preceding section, the lines of curvature are always real. Consequently, we may always choose coordinates u1 and u2 on capital S so that the lines of curvature are the coordinate curves of this system, which is allowable at any point of capital S which is not an umbilic. If we introduce coordinates of that type, then the differential equation given by the 3 by 3 determinant, which is equal to 0 that I read earlier, must be satisfied for du1 equal to 0 as well as for du2 equals 0. That is, in this 3 by 3 determinant determinant equal to 0 expanded out and as a differential equation, the coefficients of du1 squared and du2 squared must vanish. This leads to the following system of linear equations. First we have g sub 1 2 times b sub 2 2 minus g sub 2 2 times b sub 1 2 is equal to 0. And then we have g sub 1 1 times b sub 1 2 minus g sub 1 2 times b sub 1 1 equals 0. Excluding umbilics, the determinant b sub 2 2 times g sub 1 1 minus b sub 1 1 times g sub 2 2 of the coefficients of the system given by the two previous linear equations is different from 0, and in this system of linear equations has therefore only the trivial solutions g sub 1 2 equals b sub 1 2, which is equal to 0. We thus obtain the important Theorem 41.3. The coordinate curves of any allowable coordinate system on a surface capital S coincide with the lines of curvature if and only if, for this system, g sub 1 2 equals 0 and b sub 1 2 equals 0 at any point where those coordinates are allowable. We will now derive an analytic expression for the principal curvatures kappa sub 1 and kappa sub 2. If we multiply the relation quantity b sub alpha gamma minus kappa sub n times g sub alpha gamma closed quantity times L superscript alpha all equals 0, multiply this relation by g superscript beta gamma and sum with respect to gamma, we find b with the subscript alpha and then the b has a superscript beta times du alpha minus kappa sub n times du beta. This all equals 0 where beta can be 1 or 2, whence kappa sub n squared minus b with the subscript alpha and then the b also has a superscript alpha times kappa sub n minus the determinant of b with a subscript alpha and then the b has a superscript beta. This is all equal to 0. Or, since that determinant of b subscript alpha and then the b with a superscript beta all equals b over g, then kappa sub n squared minus b sub alpha beta times g superscript alpha beta times kappa sub n plus b over g all equals 0. Hence, the principal curvatures are the roots of this equation. In the relation quantity b sub alpha beta minus kappa sub n times g sub alpha beta closed quantity times L superscript alpha times L superscript beta all equals 0. To every value of du2 to du1, there corresponds exactly one value of kappa sub n, while conversely, to every value of kappa sub n between kappa sub 1 and kappa sub 2, there correspond two values of du2 to du1, as can be seen, for instance, from the 2x2 determinant involving the fundamental forms which the determinant equals 0. That is, the principal curvatures kappa 1 and kappa 2 correspond to a double root of the aforementioned 2x2 determinant equals 0 differential equations, and therefore to just one direction. The principal curvatures kappa sub 1 and kappa sub 2 correspond to a double root of the expansion of the 2x2 determinant equaling 0 in terms of the fundamental forms, and therefore to just one direction. We are now able to introduce the following two fundamental concepts. Definition 41.1. The product capital K, which is equal to kappa sub 1 times kappa sub 2 equaling b over g, that is the discriminant of the second fundamental form over the discriminant of the first fundamental form of the two principal curvatures, is called the Gaussian curvature, sometimes total curvature, of the surface at the point under consideration. And definition 41.2. The arithmetic mean of the principal curvatures given by capital H, which is equal to 1/2 times the quantity kappa sub 1 plus kappa sub 2 closed quantity, is equal to 1/2 times b sub alpha beta times g superscript alpha beta, which is equal to 1/2 times b with the subscript alpha and then the b also has a superscript alpha. This is called the mean curvature of the surface at the point under consideration. The quantities capital K and the magnitude of capital H are invariant with respect to allowable coordinate transformations. The sign of kappa sub n, and therefore also the sign of capital H, depends on the orientation of the surface. This is an immediate consequence of the geometric meaning of capital K and capital H, but can also easily be verified in a formal manner. According to the relation for the transformation for the discriminant of the first fundamental form in terms of the Jacobians of the coordinate transformation and its inverse respectively, as well as the previously read transformation law for the second fundamental form, the discriminants g and b are multiplied by the same factor factor if a coordinate transformation is imposed. Hence, capital K is invariant. The inner product b sub alpha beta times g superscript alpha beta is an invariant, but the sign of b sub alpha beta, and therefore also the sign of capital H depends on the orientation of the surface. That is, on the choice of coordinate, and you can refer back to section 34 on the normal to a surface for that one. As was shown in section 28, we always have that g is positive. In consequence of the considerations in the previous section, section 40, we thus obtained from the relation capital K for the Gaussian curvature the following theorem. Theorem 41.4. At elliptic points, the Gaussian curvature is positive. At parabolic ones, it vanishes, and at hyperbolic ones, it is negative. In section 46, we shall see that the Gaussian curvature, capital K, depends only on the coefficients of the first fundamental form and their derivatives, but not on the second fundamental form. When the coordinate curves on a surface, capital S, are lines of curvature, the equation b with a subscript alpha and a superscript beta times du alpha minus kappa sub n times du beta equals 0, where beta can be 1 or 2, that relation holds with kappa equal to kappa sub 1, du2 equal to 0, and again with kappa equal to kappa sub 2 and du1 equal to 0. Therefore, kappa sub 1 is equal to b with a subscript 1 and then a superscript 1, and b sub 1 with a superscript 2 is equal to 0, and kappa sub 2 is equal to b with a subscript 2 and then a superscript 2, and then b with a subscript 2 and then a superscript 1 is equal to 0. We thus obtain in this case that kappa sub 1 is equal to b sub 1 1 over g sub 1 1, and then kappa sub 2 is equal to b sub 2 2 over g sub 2 2, and then capital K, the Gaussian curvature, is equal to b sub 1 1 over g sub 1 1, then times b sub 2 2 over g sub 2 2, and then capital H, which is the mean curvature of the surface at the point under consideration, is equal to 1/2 times the quantity b sub 1 1 over g sub 1 1 plus b sub 2 2 over g sub 2 2 closed quantity. We finally mention theorem 41.5. The meridians and parallels of any surface of revolution of class r greater than or equal to 2 are lines of curvature. Further theorems on lines of curvature will occur in sections 68 and 88. All right, and now we have problem 41.1, the logical follow-up to theorem 41.5, prove theorem 41.5. Problem 41.1. In the particular case of a cylinder of revolution, the theorem holds as can easily be seen. Any other surface of revolution can be locally represented in the form x in terms of u1, u2, that is, in the first entry, u2 times cosine u1, and then in the second entry, u2 times sine u1, and then in the third entry, h times u2. Then the meridians and parallels are coordinate curves. Refer back to problem 28.1. We have that g sub 1, 2 equals 0, and since the determinant with in the first column x1, in the second column x2, and in the third column x sub 1, 2, this determinant all being equal to 0, and also b sub 1, 2 equals 0. From this and from the relation from theorem 41.3 where g sub 1, 2 equals 0 and b sub 1, 2 equals 0, theorem 41.5 follows. Problem 41.2. Determine the discriminant b of the second fundamental form for a sphere. Using the parametric representation of a sphere in terms of u1 and u2, we have that g equals r to the fourth times cosine squared of u2. Any normal section has the curvature given by the magnitude of kappa sub n equal to 1 over r. Hence, capital K equals 1 over r squared, and therefore b equals capital K times g, which equals r squared times cosine squared of u2. Refer back to the equation for Gaussian or total curvature capital K. Of course, this result can also be obtained from the relation b sub alpha beta equals the scalar product between negative x sub alpha and n sub beta by direct calculation. We now come to section 42, Euler's theorem and Dupin's indicatrix. The normal curvature, kappa sub n, corresponding to any direction can be simply represented in terms of the principal curvatures kappa 1 and kappa 2. Euler's theorem, theorem 42.1. Let alpha be the angle between a direction at a point capital P and the principal direction at capital P corresponding to kappa 1. Then kappa n equals kappa 1 times cosine squared of alpha plus kappa 2 times sine squared alpha. The proof is as follows. We assume that capital P is not an umbilic. We choose coordinates on a surface capital S so that the coordinate curves are lines of curvature on capital S. Then, in consequence of the relation from Theorem 41.3, that is G sub 1, 2 equals 0 and B sub 1, 2 equals 0, then the relation for normal curvature takes the form kappa n equals a fraction with the numerator of B sub 1, 1 times du1 squared plus b sub 2 2 times du2 squared all over the quotient ds squared. And kappa 1 equals b sub 1 1 over g sub 1 1 and kappa 2 equals b sub 2 2 over g sub 2 2. And this is due to the relations for the principal curvatures, the Gaussian or total curvature, and the mean curvature for when the coordinate curves on a surface capital S are lines of curvature, and these are given in terms of the fundamental forms. We can therefore write the expression for kappa n that we just obtained in the form kappa n equals kappa 1 times g sub 1 1 times u1 dot squared plus kappa 2 times g sub 2 2 times u2 dot squared. Now, the direction du2 du1 under consideration is determined by the vector x dot, which is equal to x sub alpha times u alpha dot, and the direction corresponding to kappa 1 is given by the vector x1. Since the lines of curvature are orthogonal, refer back to Theorem 41.2, and the magnitude of x dot is equal to 1, the angle alpha between the vectors x1 and x dot and the angle beta, which is equal to pi over 2 minus alpha between the vectors x2 and x dot, are determined by the expressions cosine alpha equals the fraction with the numerator of the scalar product between x1 and x dot and the denominator, which is the product of the magnitude of x1 with the magnitude of x dot, which is equal to g sub 1 1 times u1 dot all over the square root of g sub 1 1, and this is all equal to the square root of g sub 1 1 times u1 dot. We also have sine alpha, which is equal to cosine beta, equal to the fraction with the numerator of the scalar product of x2 with x dot and a denominator of the magnitude of x2 times the magnitude of x dot, which is all equal to g sub 2 2 times u2 dot all over the square root of g sub 2 2, which is equal to the square root of g sub 2 2 times u2 dot. If we insert these expressions into what we had just obtained for kappa n, we obtain the kappa n from the statement of Euler's theorem. The theorem of Euler and the theorem of Meusnier, which is Theorem 39.2, give complete information on the curvature of any curve on a surface. We may illustrate Euler's theorem in the following simple manner. Let capital P be any point on a surface capital S, such that kappa n is equal to 1 over capital R, which is not equivalent to 0 at capital P. For all directions for which kappa n is non-zero, we set the square root of the magnitude of capital R then times cosine alpha equal to x1, and similarly the square root of the magnitude of capital R then times sine of alpha equal to x2. That is, we consider a plane with Cartesian coordinates x1 and x2 and lay off from the origin of those coordinates segments of the lengths, the square root of the magnitude of capital R of alpha in the direction whose angle with the x1 direction is alpha. The directions of the coordinate axes thus correspond to the principal directions on the surface at the point capital P under consideration. In this manner, we obtain the so-called Dupin indicatrix. An analytic representation of this indicatrix can be simply derived as follows. If we multiply both sides of kappa n from the statement of Euler's theorem by 1 over the magnitude of kappa n, where kappa n is non-zero, then in consequence of the radialesque coordinate axes corresponding to the principal directions on the surface at P, we find that kappa 1 times x1 squared plus kappa 2 times x2 squared is equal to positive negative 1. If the point capital P under consideration is elliptic, kappa 1 and kappa 2 have the same sign and the indicatrix is therefore an ellipse. If capital P is hyperbolic, kappa 1 and kappa 2 have different signs. Then the indicatrix consists of two hyperbolas which have the same asymptotes. This is the reason for the names elliptic and hyperbolic point, and it also justifies the name asymptotic directions, since these directions are the directions of the asymptotes of the indicatrix. As an immediate consequence of the above consideration, we have Theorem 42.2. The principal directions bisect the angles between directions corresponding to the same normal curvature, in particular the angles between the asymptotic directions. If kappa 1 equals 0 and kappa 2 is non-zero, the point capital P is parabolic. In this case, we obtain from the relationship between the principal curvatures and the coordinates, x2 squared is equal to positive or negative capital R2, where capital R2 is equal to 1 over kappa 2. That is, the indicatrix consists of a pair of straight lines parallel to the x1 x1 axis through the points positive or negative square root of the magnitude of capital R2 of the x2 axis. The Dupin indicatrix at a point capital P of a surface capital S is closely related to the intersection of capital S with planes parallel to the tangent plane capital E of capital P to capital S at capital P. Indeed, when we choose two such planes which lie on both sides of capital E of capital P at a small distance epsilon, then according to Theorem 40.1, the intersection of capital S and those planes is given by 1/2 times b sub alpha beta times du alpha times du beta, which is equal to then plus or minus epsilon, neglecting terms of third and higher order in the magnitude of du1 plus the magnitude of du2. If in particular the coordinates are chosen so that the coordinate curves are lines of curvature on capital S, then the previously obtained relation takes the form b sub 1 times du1 squared plus b sub 2 times du2 squared is equal to positive or negative 2 times epsilon. But because of the principal curvatures, the Gaussian or total curvature and mean curvature relations for when the coordinate curves on a surface capital S are lines of curvature, and these relations are then given in terms of the fundamental forms, then what we just obtained is equivalent to kappa 1 times g sub 1 times du1 squared plus kappa 2 times g sub 2 times du2 squared, which is then all equal to positive or negative 2 times epsilon. Hence, we have Theorem 42.3. The intersection of a surface capital S of class R greater than or equal to 2 and a plane which is parallel to the tangent plane capital E of capital P to capital S at a point capital P and near to capital E of capital P is approximately a conic section which is similar and similarly placed to the Dupin indicatrix at capital P, or if capital P is a hyperbolic point, to one of the two hyperbolas constituting the Dupin indicatrix. In the case of a hyperbolic point, capital S intersects both planes, while in the case of an elliptic or a parabolic point, capital S intersects only one of the two planes. We see that at an elliptic, hyperbolic, or parabolic point, a surface looks approximately the same as a portion of an elliptic or hyperbolic paraboloid or a cylinder, respectively. Section 43. Torus. A surface obtained by rotating a circle about a coplanar line outside of the circle is called a torus. We may illustrate all types of points, elliptic, parabolic, as well as hyperbolic ones, on this surface. We rotate a circle capital C of radius r lying in the x1, x3 plane with center at x1, x3 equal to r0, 0 about the x3 axis. We denote by u2 the directed angle from the positive direction of the x1 axis to a point capital P on capital C. We may then represent the torus capital S in the form x in terms of u1 and u2 equal to, element-wise, the quantity r0 plus r times cosine u2 closed quantity times cosine u1, and then in the second entry, the quantity r0 plus r times cosine u2 closed quantity times sine u1, and then in the third entry, r times sine u2. See figure 52 on the next page. The coefficients of the first fundamental form are g sub 1 equal to the quantity r0 plus r times cosine u2 closed quantity squared, g sub 1 equal to 0, and g sub 2 equal to r squared. Therefore, the discriminant of the first fundamental form g is equal to r squared times the quantity r0 plus r times cosine u2 closed quantity squared. The coefficients of the second fundamental form are b sub 1 equals negative quantity r0 plus r times cosine u2 closed quantity times cosine u2, b sub 1 equals 0, and b sub 2 equals negative r. Since g sub 1 equals b sub 1 which both equals 0, the coordinate curves are lines of curvature on capital S. Refer to the relation from Theorem 41.3, namely g sub 1 equals 0 and b sub 1 equals 0. Hence, by the relations for the principal curvatures, Gaussian or total curvature and mean curvature for when the coordinate curves on a surface capital S are lines of curvature, and then given in terms of the fundamental forms, we have that kappa 1 equals b sub 1 over g sub 1, which is equal to the negative fraction with a numerator of cosine u2 all over a denominator of r0 plus r times cosine u2, and kappa 2 equals b sub 2 over g sub 2, which is equal to the negative reciprocal of r. Consequently, we have that capital K is equal to b over g, which is equal to kappa 1 times kappa 2, which then is equal to a fraction with the numerator cosine u2 all over a denominator of r times the quantity r0 plus r times cosine u2. If u2 equals positive or negative pi over 2, then capital K equals 0. That is, the circles of radius r0 on the torus capital S consist of parabolic points only. Points on capital S whose distance from the x3 axis is greater than r0 are elliptic, while points whose distance from the x3 axis is smaller than r0 are hyperbolic. We finally mentioned that the torus has the total area, capital A equals the double integral with the outer integral being from 0 to 2 pi and the integral being from 0 to 2 pi of the integrand, then quantity r0 plus r times cosine u2 closed quantity times r, and then the integrals are in terms of du1 and then du2. This is equal to 4 pi squared times r0 times r. This result can be obtained more simply by the Theorem of Pappus. The area of a surface of revolution is equal to the product of the arc length, lowercase s, of a meridian capital M, in our case, lowercase s equals 2 pi r, and the length capital L of the path of the center of gravity of capital M when capital M is rotated through the angle 2 pi. In our case, capital L equals 2 pi r0. All right, and I think I'll leave it there. Thanks for watching, everyone, and I'll see you guys in the next one. Peace.